Hello. These are the review slides for the final exam for spring 2018. So we're going to go through these. The questions are going to be just like this, with that no multiple choice. So you're just going to walk through these. So no craziness. So for this one, calculating formal charge. So remember, um, it's going to with formal charge. It's valence electrons minus the electrons it has now. So for lone pairs, right, those just stay with the atom that they're on. But for each bond, remember there's two electrons, right, and we're going to slice those in each one of those in half. So the oxygen now looks like it's lone pairs, and then one electron from each of its bonds. Okay? So valence electrons, right? So you count over. So oxygen normally would have 6. Subtract what it has now, which is 1, 2, 3, 4, 5. And so it's a plus 1. For the resonance structure, remember that in order to be able to participate, right, it has to satisfy at least one of three conditions. It either has to have a charge, with some notable exceptions, namely the quaternary nitrogen. It needs to have a set of lone pairs, or it has to be part of a pi bond. Okay? It has to have part of a carbon-carbon double bond, carbon-oxygen double bond, carbon-nitrogen triple bond, whatever. As long as it satisfies at least one of these, it can participate in the resonance structure. Okay? So for this one, usually what you want to do is draw in the hydrogens. Right? So each one of these has 3 bonds shown, so each one has a hydrogen. Around here, you have this carbon here has a charge to it, so it's going to participate. These 2 carbons have a part of a double bond, so they're fine. Here's another double bond, they're fine. But this one here, it's just a regular sp3, it's a regular alkane. So that carbon itself isn't going to be able to participate. So for this one, so after you figure that out, you have to, it's usually a good place to start with where the charge is. So for here, this carbon has only 3 bonds, right? One's 4, so it needs to look to its neighbors for help. So for this one, this carbon here can't help, but this one can by sliding those electrons up there. And so you're going to end up with bonds here. Drawing your hydrogens. Right? So now this carbon has only 3 bonds. So it needs to look to its neighbors. Now we could slide this back, but that would just be here. So we can just keep going around the ring. And so we can always slide those electrons over. And so you end up with now technically you don't need to draw these hydrogens in, but it's usually a good habit to. So for now we've got a positive charge here because this carbon has 3 bonds. And so since this carbon can participate, we're done. We've gone and worked with all the atoms that can participate in this in the resonance structure. So for this, for the hybridization, remember we look at bond sets plus lone pair sets. And that's going to tell you how many letters we need. For that, you go with S, and then you start adding P's until you get all the letters you need. So for this one here, right, we have 2 lone pair sets plus 2 bond sets, right? So this one and this one. So we need 4 letters. So it's S, P, P, P. Right? So it's sp3. So for this one here, we don't have any lone pairs, right? But we do have 2 bond sets. We have one here and one here. Okay, so each, in in this case, a double, single, and triple bond each correspond to an individual set. So with that, so here we have two sets. So we need two letters, so it's just SP. Okay, so for this one, so you're going to be given an IR spectrum and two structures, and you have to tell me which of these structures corresponds to this IR spectrum. Now, you're always going to have the alkane CC and alkane CH bond or signals, so I don't list them. Okay, so I am going to give you the chart. So for 1650, that's going to be here. Then the rest of these, no, it's not going to be diagrammatic. There. Okay, so the other one would be the 3050. So for this one, it could be this. Could be this. Oh, wait, no. For 3050, nope, can't be the OH. That would need to be 3500. Or the NH. So this is really the only thing it could be. So so this one would correspond to the to a carbon-carbon double bond. This one would be the H, the CH bond off of an alkene. So that's going to be this one. Now don't forget that the IR is both what's there and what's not there. So again, if you had this structure, if I had given you this third one, say that structure there, this one would only be 1650, right? Because there are no H's hanging off of the double bond, right? They're all carbons. So had I given you that IR spectrum, but just the 1650, it would have been this one. But because it's 1650 and 3050, it's got to be this one. So be careful. I am going to give you this chart so you don't so for this one, circle and name the functional group. So you point for circling it correctly, you point for naming it. You don't have to worry about alkanes, cycloalkanes, and so here, right? So here you have a C double bond O. And so you have to be really careful about what's on either side of it. So you have a carbon on one side, and you have an O carbon on the other. So that even though this is benzene, it doesn't matter. So that makes this here, benzene. Here's an OH, but it's just hanging off of a regular CH2. So that makes this a bond. If this was a C double bond O, you'd put a sulfuric acid. If this wasn't here, this was bonded directly to the benzene. This one has that CH2 in between. Benzene here, and nitrogen. Look at that. So since we have a triple bond C, nor do we have a C double bond O here. That makes this. We have a C double bond O, so here, adjacent to it. Okay, so the pair of molecules is most acidic. So since this is going to be the, when you're looking at the hydrogen, the acidic hydrogen, you have to figure out what atom it's hanging off of. So the one closest to iodine is going to be acidic. So that makes this phosphorus more acidic. This is below nitrogen here too. Now, as I said, also with hybridization, right? So sp atoms are going to be more acidic than sp3. So this would be terminal alkynes versus alkenes. Yeah, so if you have an adjacent carbon, it's going to make it much more acidic. Whether it's a with an OH, you can see this here, just regular alcohol pK of 16, but if you add this to a C double bond O here, it becomes a carboxylic acid. Right? It's even in the name. And a phenol here, you've got the bond right here adjacent to it. It's carbon-carbon double bond, but that's fine. You can also have these inductive effects. So like that. So if you have an electronegative atom near it, the bond, or near where the acidic hydrogen is, the closer it is, the more acidic. Right? So as it moves away, it's going to become less acidic. So. Okay, so for naming the molecules, I'm not going to go over this in this slide deck. The best thing to do is go back and take a look at chapter 4, where we walk through all of these. So. Okay, so for cis-trans or cycloalkanes, right? So you've got the ring, and are they above or below the ring? So for cis, they're either going to be both below or both above. For trans, you're going to have one up, one down. So over here, right? So with that, so we've got they're both below the ring. So this should be cis. For here, here's the ring. So with that, so one below, one above. So this should be trans. So for the degree of unsaturation, I am going to give you this formula on the equation sheet. So for that, I'm not going to give you the key. It's just going to be that formula. But for this one, right, so this is for DOU. So it's 2 times the number of carbon atoms. So in this case, it's 8. Plus 2. So that's a constant. Plus the number of nitrogens, which in this case is 1. Minus the total number of halides, right? So that's fluorine, chlorine, bromine, iodine. So in this case, we just have the one fluorine, so it's minus 1, minus the number of hydrogens, which is 8, all divided by 2. Notice we don't have oxygen in here, okay? Even though we have an oxygen here, so don't include it in your equation. So this ends up being, let's see, 16, 19, minus 9, divided by 2, so it's 10 divided by 2, so it's 5. So find the chiral center. So what you want to do is go ahead and draw on your hydrogens, right? So well, here's your carbons. Okay, so this one has 1 bond shown, so it's a CH3. 2 bonds shown, so CH2. Right, this carbon has 1, 2, 3 bonds shown, so it's a CH. Here it's 2 bonds shown, so CH2. CH2. Here it's a CH, and both of these are CH3. Okay, so anything that has multiple hydrogens on it, so that can't be a chiral center. Right? So you can get rid of those. Okay. So really, we just have to check out this one and this one. Okay, so for here we have fluorine, hydrogen, CH2, CH2. That's a tie, right? So what do? We then compare, go one out. We have CH2 and CH3, right? That means this side is different from that side. So we're going to have a nice big chiral center here. Okay? So there's one there. So we come over here, right? So we have a CH2, CH3, CH3. Notice how we have 2 CH3s? Okay, that means that these two are the same, so there's no chiral center there. So that's the only one we have. Okay, so determining RS configuration. Okay. So you need to do the 4 priorities. Okay. So we have a carbon, a carbon, a carbon, and a hydrogen. Okay, so we don't know. We know that the carbon groups are going to be 1 through 3, right? The hydrogen, because it's the least, it's not the heaviest, it's the lightest, right? So we know that that's going to be number 4. Okay, so for this one, right, so this has 2 bonds, so it has to be CH2. This one also has to be a CH2. 2 bonds are shown. Here, all 4 bonds are shown, so we're good on that. So we're going to compare the bonds. So for this one versus this one versus this one, For here, we have two carbon-carbon bonds, two carbon-oxygen. Here we have two carbon-carbon, two carbon-hydrogen. Here we have two carbon-carbon, two carbon-hydrogen. So for the heaviest bond in this case is carbon-oxygen versus carbon-carbon, carbon-carbon. Right? So that oxygen's heavier than carbon, so this is going to be number 1. Okay, but here, these two, it's a tie. So what do? We go out one further. Okay, so now we're going to compare this carbon versus that carbon. Okay, here, 2 bonds are shown, so it's CH2. Here, 2 bonds are shown, so it's CH2. So this one, right, so we have 1 carbon-carbon bond, 2 carbon-hydrogen, 1 carbon-chlorine bond. Here, we have 2 carbon-carbon, here and here, 2 carbon-hydrogen. So the heaviest bond in this one's carbon-carbon. Here, it's carbon-chlorine. Doesn't matter. So this is heavier, so this wins. Now, it doesn't matter that this has 2 carbon-carbon. It doesn't matter. It's carbon-carbon versus carbon-chlorine. So this is going to be 3. This is going to be, oh, excuse me, this is going to be 2. This is going to be 3. Now, if you're going to do the hand method, right, your thumb needs to go with 4, and so your fingertips need to start at 1, so it can come up here. So the 4 is coming out at you, at the camera, so that's where your thumbs are going to go. And so if you start with your left hand, right, it needs to start at 1. So 1, 2, 3. So if you just go to 1 to 2, you're fine. So 1 to 2. Notice how my fingertips are curling 1 to 2. Okay, since I'm curling with my left hand, that makes this an S. Right? If I try to curl 1 to 2, right, 1 to 2 like that, I'm going to break my fingers. Now, if you do the steering wheel method, okay, so we're going to say this is 4, so 1, 2, 3. So we have to get the this in the back. So you need to flip this around, so it ends up being, so 1 stays where it is, but 2 and 3 flip. So 3, 2, 1, so that 4 is behind. Since we're going kind of clockwise, it's an S. So it doesn't matter which way you do it. You can get the same way, but you have to remember that if you're going to do the steering wheel method, you have to get 4 going on the wedge, or excuse me, on the dash. It's on the wedge now. So easy with alkenes. Right? So with that, so you're going to want to slice this in half, and then look at this carbon versus this carbon, the high and the lows. So from this side, right, we've got chlorine versus nitrogen. Chlorine's heavier, so this is going to be the high. This is going to be the low. So on this side, right, we have CH2 versus CH2. Right? Carbon versus carbon, it's a tie. 2 carbon-carbon, 2 carbon-hydrogen. Right? 2 carbon-carbon, 2 carbon-hydrogen. Right? It's a tie. So now we're going to have to go out to here versus here. Right? So this is a CH2. This is a CH3. This one has 2 carbon-carbon, 2 carbon-hydrogen, 1 carbon-carbon, 3 carbon-hydrogen. So they're both carbon-carbon, but this side has 2 of them. This one only has 1, so this is the high. Since the high sides are on the same side, they are on the same side, right? That makes this Z. They are on the same side. Okay, so for design and synthesis, right, you're going to have to pick your carbon bits from over here. Okay, so here is your triple bond. So there's the triple bond, so it's either here, but you're going to have to rip off one of these hydrogens, right? So let's say we rip off that one. That would mean the other side, right, would have this. Okay, we need a hydrogen on there. We don't need a methyl. If we had a methyl here, we'd pick this one. And instead, we're going to need to start with this one. So we're going to start with acetylene here. We're going to throw in sodium amide. That is going to rip off this hydrogen. You're going to make sodium's here. You're going to make ammonia. Now, so this carbon and this carbon are part of that acetylene and that hydrogen. We still need a 2-carbon piece. And so for here, we come over here. Where's an extra 2-carbon piece? Well, it's right here. There's 2 carbons here. We're going to make this connection where that bromine is. Okay, so ultimately, you're going to make here like that. So these electrons, this lone pair here, become this new carbon-carbon bond. So you end up making bromine plus minus. There you go. So be careful. So these are the alkyne reactions to do. This is just the ones we were doing for the design of synthesis. The other ones would be if you just have excess hydrogen in the presence of palladium on carbon, you're going to go to a single bond by adding hydrogens across it. If instead you had that reaction and you poison the catalyst either by using the barium sulfate or with a Lindlar, you're only going to be able to go to the double bond, but the hydrogens are going to get added on the same side because remember the hydrogen gets loaded onto the catalyst surface and the molecule comes in, grabs them, pulls them away. They're going to add to the same side. So you're going to make the cis. With this one, for here with lithium and ammonia or sodium ammonia, similar product figure, but now we're going to get the trans double bond. So do be careful. Okay, so for classifying these, right, so the first thing you have to do is to figure out is it keto or alto or aldo. And so here's a C double bond O. Right, there's carbons on either side. So this would be a keto. For here, you have hydrogen hanging off of the double bond, or C double bond O. So this is the aldo. It's the aldehyde. So now you need to count the total carbons, right? So it's 1, 2, 3, 4, 5. Don't forget the one underneath C double bond O. 6, 7. So it's a keto heptose. And again, I'm going to give you this. So there. Here it's 1, 2, 3, 4, 5, 6. So 6 hexose, so it's an aldo hexose. There you go. Okay, so is it the sugar in the DL configuration? So for the straight chain, all you have to do is look here at the last chiral center. Here. If it's in this case, right? So if it's that way, if it's to the right, it's D. If it's to the left, it's L. Okay, left L. So for here, it's going that way, so, right? So it's D. Here it's pointed to the left, so it's L. Here it's pointed to the right, so it's D. Now for the cyclic versions, right, you're looking at this carbon group that's hanging out. Okay? If it's below the ring, it's L. So below it's L. Here it's above the ring, so it's D. There you go. Okay, so for this one, first thing we have to do for naming the linkages is get those numberings in, stuff like that. So we have a 6-carbon sugar, right? We have a 6-membered ring, so that makes this 6. So we're going to go 6, 5, 4, 3, 2, 1. If you get to this point and it's not 1, something's gone wrong. Most likely what's happened is you've missed this carbon here. So for here, it's going to be 6, 5, 4, 3, 2, 1. 6, 5, 4, 3, 2, 1. And 6, 5, 4, 3, 2, 1. Okay. So for each linkage, you just sort of look at that atom in isolation. So you're just looking at these two sugars. Okay, this is the one on the right, or excuse me, this is the one on the left, stuff like that. So the bond is going down from left to right, stuff like that. So that makes it an alpha. Right? I forgot to mention this. So the apple falls from the tree, so the alpha falls from the tree. So with that, so it's going the alpha from carbon 1 to carbon 6. So it's an alpha 1, 6. So for this one here, you just, again, you can look at them in isolation. So for that, so for here, the left, this is the left sugar. It's going up. So this is going to be beta. 1 to 4. So it's from carbon 1 to carbon 4. Now for this one, right, again, you're going to be looking at this in isolation. This is the left-hand sugar now. Right? Since the bond is going down, it's alpha. And so it's alpha 2 to 6.